Okay, so I did send you home with a take-home problem, right? And I'm hearing that was a little rough on the second derivative. Okay. Here's what I'll do. Do you think you need more time, or is it that you're stuck?
I just have like a few questions.
You just have a few questions on it? Okay, let's do this. Let's hold off on it for now, and maybe at the last 10 minutes of class we can address that, okay? I won't collect it right now, but I'd really prefer if you weren't trying to do it right now and like pay attention to this, and then at the end we'll kind of discuss it. Just don't let me get, at like 10:05, like stop me, all right? Okay, just as a reminder, we have a test the week we come back from spring break on Thursday. So hopefully you won't go to too hard on spring break, and you'll remember everything when you come back. Hopefully. We'll see. I apologize on the video from last class. The first half, everything was fine. Second part of class, I forgot to unmute my microphone. So anytime that we take a break and I let y'all work on a problem, I usually mute my microphone, and I've been forgetting to unmute it. So if that happens again, and you do something in class, just someone remind me, hey, unmute your microphone. Hopefully it won't happen again. All right, so today, this is a reminder of what we've already done, and I think I put this on the board last time also, but there's something I want to point out that we have not discussed. We know that the first derivative tells us where our function goes up and down, right? Second derivative tells us about the concavity, the shape of the graph, whether it looks like a smile or a frown, right? And we could use that information about the up and down or down and up to find local maximums and local minimums. And I've underlined the word local here because what we're going to be talking about today is what's called the absolute maximum and minimum. And so I want to really kind of stress with two pictures here the difference between a local max and a local minimum. So when you look at this graph, this point right here is the highest point on the graph locally. Like if there was a person standing right here on top of this, they'd be the king of the mountain, right? Of that mountain, right? Locally, that would be the highest point. It's not necessarily the highest point on the entire graph. You can see that if I go over here, there are a bunch of points that are higher than that point, right? So this is not the highest point on the entire graph, but it is locally the highest. Does that make sense? And then this point right here is a local minimum. Same story. Is this the lowest point on the entire graph? This point? No, it's not. There are points over here. The arrow means it keeps going down. So these are only given, this right here only gives us information about what's happening locally. Today what we're going to do is we're going to find what's called the absolute maximum and minimum of a function. But to be able to find the absolute max and min, we have to restrict our actual function domain. We have to start it and stop it somewhere. And this is okay because in business problems, a lot of times, the X might be like the number of skateboards you sell or something, right? Whatever your company is selling. So it doesn't make sense to have negative skateboards. And so maybe you start at 0, or maybe you start at 1. And then you go to some reasonable number, like you're not going to sell more than 1 million skateboards, right? So you stop it somewhere. And so if we can start it and stop it somewhere on some closed interval, then our function must have a highest point and must have a lowest point. Make sense? And how do we go about determining the absolute max and absolute min? So let's talk about this point right here. This point right here would be a local minimum because it is the lowest point in this little area, like this little region. Do you agree that's the lowest point? This right here would be a local maximum. And we could actually find that from this, doing this. We could find where that happens. This would be a local, what? Minimum. I'm just put L min, is that okay? And then here, this would be a local max. And then this point right here would be a local minimum, right? But there are only 2 points on the graph that can be the absolute max and absolute minimum. And is it obvious where they are? Yes? One of those local maximums, one of the local maximums is our absolute, right? So this right here is our absolute maximum. And what about our absolute minimum? The far right point, yes? Okay. So this would be our absolute minimum. So what we're going to go about doing now, today, is we're going to try and find these 2 points, all right? So the way we're going to do this is a little bit different than what we had done before, all right? The technique involved with this is a little bit different than this. This we had to do number line, test points, all that stuff. This is actually going to be a little bit easier to do. Even though it looks like it might be harder, it's going to be easier to actually do this than it is to do this. All right? So let me just write something on the board first, and then we'll do our first example. Any questions on what we're trying to do? No? This is also probably a little more applicable to the real world. Like if you have a function that represents profit, you do want to know where that highest profit is and where that lowest profit is. You don't want local high and low points. You want the absolute highest and lowest points. Okay. A continuous function f on a closed interval AB must have an absolute max and min. Okay, must. But we have to have a continuous function. Do you remember what it meant to be continuous? We talked about it briefly in here. Just means you can draw the function without picking up your pencil. You remember me talking about that? Okay, so if you have a function that you can draw without picking up your pencil, and you start it somewhere, doesn't matter where, and you draw without picking up your pencil, and you stop it somewhere, you are guaranteed to have a highest and lowest point. All right? There's no way around it. You have to have it. The only exception to this you might have is if you draw a flat line. Because if you draw a flat line, that is continuous. And in this case, all the points have the same value, don't they? And so your highest and lowest points are the same value. It's the same. Your max and min is exactly the same. That would be the only exception. But this is a very boring example because you're never going to be dealing with a profit function that's just flat, right? You're never going to have that. So when I state this, understand that this is a special case. We won't even deal with it. Okay? Now, that's just to let us know that yes, it's got to happen, all right? Here's how to find them. To find absolute max and min, here's what we do. First, we find the solutions to f prime of x equals 0. Now, did we do that in the previous sections? When we were trying to figure out local max and min, didn't we take the derivative and set it equal to 0? So that's the same thing, right? And then we did all number line and all that stuff, right? Not the case anymore. Step 2. Evaluate f, the original function, at the critical numbers those are the solutions from part 1. Okay, so when we talked about critical numbers a couple of days ago, we defined the critical numbers to be wherever the derivative was 0. All right? So what we're doing is we're going to take the answers we get from this and we're going to evaluate the original function. We're going to just take these answers and plug them into the original function. No number line test points. No, this is what students get confused. They're like, am I supposed to be doing test points? No, on this, you just take these answers and plug them into the original function. Okay? And it's going to spit out some number. And one more thing. And evaluate f at the endpoints. The largest answer is the absolute max. Smallest is absolute minimum. And that's it. It's really just like a two-step process. We're going to work through an example so you'll see what I'm talking about. But let me try and explain why we only have to do this minimal amount of work to be able to recover the absolute max and min. Think about a couple of different scenarios. Let's say I have a graph. If I draw it like this, start here, continuous, not going to pick up my pencil. There, I just did it like that. Y'all see the absolute max, right? Right here? That's your absolute max right here. Where did it take place? Where did that happen? Was that at a critical number or was that at an endpoint? Is this happening at a critical number where the derivative is 0, or is it happening at one of the endpoints? At a critical number, right? Now, where's the absolute minimum? The left endpoint, right? This is your absolute minimum. So that took place at an endpoint, right? No matter how I draw a graph, it's either going to happen at a local max, at a critical number, anywhere where our derivative is 0, or it's going to happen at an endpoint. I challenge you to draw something without picking up your pencil from one point to another, and it have a max or min, an absolute max or min that is not at one of those places. Does that kind of make sense? Like there's no way to do it. It has to happen at one of these places. It's either at a critical number or an endpoint. Let me try and draw another one. What about this one? If I draw this, where's the absolute maximum taking place? At the first endpoint, right? Where's the absolute minimum? At the other endpoint, right? There's a bunch of local maxes and mins in here, but the absolute max and min happen at endpoints. So you could have a function that the two endpoints are where you have the max and min. Is it possible to have one where the endpoints don't come into play at all? How about this? Look at this. Absolute max, absolute min, the endpoints didn't factor in, did they? I mean, they were not where it happened. So that's why when we do this, all we have to do is just test anywhere we have the derivative 0 and the endpoints. And all we're doing is we're comparing them. So when we say plug them in, I'm actually finding these values. That one right there, that one. And what I'm doing is I'm taking these numbers and I'm plugging them into the original function. So imagine if I plug this number in, I'm going to get some number out, right? Then I get this number in, I get some number out, this number in, some number out, this number in, some number out. I just look at those numbers. The biggest number I get is going to be my max. The smallest I get is my min. Got it? Y'all seem thrilled. All right, let's do one. See, there's no second derivative involved in this at all, which is probably good news. Okay, so let's do, yeah, we'll do that one. Let's do f of x is equal to x cubed plus 3x squared, and then minus 9x minus 7. So there's a function, right? Right now, if I ask you for the absolute maximum and absolute minimum, you would not be able to give me an answer. Because what I need to do now is give you an interval to look at it. Right? I need to tell you where to look. If you were to graph this function right now, it would do something like this, okay? And you had arrows, it would go down, it would go up. So I need to give you an interval to just kind of like focus your attention only to a certain place, all right? So let's do the first one, -6 to 4. Okay, so you're only allowed to be looking in that window between -6 and 4 and tell me what the highest and lowest points on that graph will be. Try and take a step back if you can. I don't know if you'll appreciate this as much as I do. But imagine on the first day of class, if I would have walked in here and put this polynomial function on the board and said, hey, look, I want you to think of all the different x's you could plug in here between these two numbers. You're only allowed to pick numbers between here and here. And I want you to tell me the biggest number this is going to spit out and the smallest number this is going to spit out. That would seem like a monumental task, wouldn't it? Okay, what we're going to do right now is going to allow us to find that. That's what we're doing, all right? So, yeah, I think I do appreciate it more. Yeah. Okay, here we go. First step, derivative, right? So, are y'all comfortable with this product, or not product rule, the power rule? Like derivatives of these, are y'all to the point where it's just like, okay, this is, all right. It's just when it becomes like product and chain, and that's when it becomes more complicated. All right, so I'm supposed to take that and set it equal to 0 now, right? So I take this, and if I were doing this problem, which I am, I would factor a 3 out just because I noticed they all have a factor of 3. And then can't I just cancel this 3? Right? Because I could really just divide both sides by 3 at this point. So really I'm trying to solve this quadratic equation. And when it comes to solving quadratic equations, we have several techniques. We've talked about this before. You can factor, or you can use quadratic formula. All right?
No, I'm confused. Are you
Okay.
looking for the derivative of function x?
No, I took the derivative from here to here, right?
Okay, aren't you missing the 3x squared though? Oh no, I'm sorry. Oh no, I'm
From here to here? I pulled a 3 out of all.
no,
You
I
good?
missed something. I was super confused at first, but now I got it.
You're good. Okay. See, I could tell by looking at
No,
you
yeah,
something
I
was
was
wrong.
confused at first.
Okay. Well, I like it when I can tell. When I can't tell, that's when it's difficult. So I'm like, are y'all okay? All right. So this does factor. What does this factor to be? X plus 3, x minus 1. And now you get 2 solutions, right? These are our critical numbers. Now, there's a very important step right now that I did not stress to you when I was writing down the steps, and maybe you want to add this into the steps as a side note. When you get these solutions, you must check to make sure that they live inside the interval you're looking at. Because if, like, let's say this came out to be like x is 10, you would not want to go plug 10 in to your function because 10 isn't in here, right? So let's do a quick check. You know, are these in the interval -6, 4? So are they? Are they both? Yes. Now, if one of them wasn't, we would just scratch it out, okay? All right, next step. What is step 2? I found the critical numbers. What's step 2? I'm going to plug those numbers into the original function right now, right? So step 2, I'm going to find f of -3. I'm going to find f of 1. I'm going to find f of 2 more things. What? -6 and +4. So I'm evaluating my function at the critical numbers, and I'm evaluating the function at the endpoints, right? And that's it. The absolute max and the absolute min has to be from this list of 4 numbers. So why don't you go ahead and do that? I'm going to give you about 2 minutes, 3 minutes maybe, to plug those in to here, and then we'll just check. While you're doing that, I'm gonna graph this. Y'all get them yet? Can you all see that graph okay? After I erase this stuff. That's the entire graph, right? That's the entire graph drawn out there. What did y'all get for these answers? What's f of -3? Anyone? Anyone?
-34.
-34? Anyone else?
Oh, -20.
No. Negative 20? 20. Okay, 20 sounds like the winner. How about f of 1? Negative what? Negative 12. I'm going on consensus here. I don't know if these are right. Negative 6? Negative 61. And last one, f of 4. 69? Okay, I need to open up this window. Oh, I'm sorry, man. I'm sorry. You all right? Okay.
Oh yeah, sorry.
It's all right. You don't want to do all the other work and then take your time on this, right? Okay, so look at the graph. This is the whole graph, right? But we're only supposed to be drawing it from negative 6 to 4. Is that correct? Negative 6 to 4? I still messed up. What was it at 4? Oops. There we go, that's better. Okay, I think that's a better look at it there. So at negative 6, you said we were down here at negative 69, somewhere in here, right? And then we follow this graph, right? And we stop at 4, and 4 puts us right up there. Right up there. Yes? Okay. So we found all 4 of those points, right? The 2 endpoints and these 2 points, and we evaluated the function. But without the graph, we could tell anyone the answer, right? What is the absolute maximum value of this function? 69. Where does it happen? At what x value? 4, okay? And what is the absolute minimum? Negative 61. So this is your absolute minimum, right? This is your absolute maximum, and it occurs at negative 6. So it actually occurred at the 2 endpoints here, didn't it? There's no other points that you could plug in between negative 6 and positive 4. There's nothing else you could plug in to ever get a value bigger than 69 or less than negative 61. Make sense? Okay. Now the next question I'm going to ask is the same exact problem, okay? So I'm going to give you that function again, but this time let's look at it on the interval negative 2, 2 instead of negative 6, 4. So how would that change things? Well, we would still go through and we would set the derivative equal to 0, wouldn't we? And that would give us the same 2 answers, because that work would be identical. And what were our 2 answers? Negative 3 and positive 1, right? At this point, you would check to make sure these lie in this interval, do they? Not both of them, right? You would have to eliminate this one. Do you see what I mean? That's a critical step, because if you don't eliminate it, you're going to think that you're going to have something going on there when you're not allowed to look there. So now step 2 would be to evaluate my function at what points? At 1, and then at negative 2, and at 2. So at the 2 endpoints, and at the only critical number that lived in there. And I would compare these. And we already did f of 1. What was f of 1? Negative 12. Now these we had not done, right? 15 and negative 5. So let me draw the graph. I'm only supposed to go from negative 2 to positive 2, which is right there. So I'm only looking at the graph between here and here. Do y'all see the difference between this one and the previous problem? So it looks like we have, what, this is our max right here? And it happens at negative 2, right there. And then we have our, what is our minimum? This one? Absolute min. And that happens at 1, so you can see it right there. You see how that works? Okay, would you mind turning the projector off? Bottom left corner. There you go. That's pretty much it. That's the idea behind this. So let's do one more of these. We're going to do one more of these together, and then I'm going to let you do one yourself. And I'm going to mute the microphone, and someone's going to remind me to unmute it. All right, let's try this. Let's go. F of x is x to the 4th minus 8x squared plus 16. And I would like for us to find the absolute max and min on, let's start with -1, 3 first. So first step, derivative, right? So what is my derivative? That's you. 4x cubed minus 16x, and that's it, right? This will be interesting. Now I need to take that derivative and set it equal to 0. And how would you go about solving that? Take out a 4x first. If I factor a 4x out, what will I be left with in the parentheses? Yes, that will happen in a second. I'm gonna, well, not with 4 though, hold on. You have x squared minus 4 when you pull the 4x out, right? You have x squared minus 4. And then that is a difference of squares. This is a difference of squares. So you have to recognize that pattern. That factors to be x plus 2 times x minus 2 equals 0. And now we set each of those equal to he continues to bring life to this class, doesn't he? All right, set each of these factors equal to 0. Set that to 0, you get 0. Set that to 0, you get -2. Set that to 0, you get 2. And now, all right, hold on. You got to be able to do something with that. I don't know how to turn these off.
You can turn them off right here.
Here, where is it? Right there.
I just hope they don't come out something else. That's what I'm hoping.
Yeah. All right, so now what? We've got the solutions, now what? Plug them into the original? Check them first. Do any of these lie outside this interval? -2 doesn't work, right? -2 is not in there, so I don't want to use that one. So that's it. I'm just going to plug in for step 2. I'm going to plug in this. I don't know why that reminds me. I saw this video of a a city council meeting where, for some city, I don't know where it was, they had a city council sitting up there and they're recording the session, and one of the guys from the city council goes and gets up and goes to the restroom, but he doesn't realize his microphone is on the whole time and it's playing over the PA system. Hilarious. Somebody go get him. Someone go in there. You can hear toilets flushing and it's funny. All right, so I plug in the two critical numbers and the two endpoints, right? Don't forget the two endpoints, and you get to plug them in there. So get 16. That was the easy one. 2, 16, 0. -1, 7, 25. Okay. Trust those answers. What is the absolute maximum? 25. Where does it happen? At 3, right? Okay. And that happens to be an endpoint. That doesn't matter, but this is your absolute max. And then your absolute minimum is 0, right? Absolute minimum. Pretty straightforward? Okay. I'm going to give you one to work, all right? And then after that, we'll move on to the next idea, next topic. That's it for this section, though. It's pretty straightforward. Okay, so how about we try and kill a little bit of your homework here. How about you take, this is a homework problem, 2x cubed minus 3x squared minus 12x plus 24. And for your homework, they ask you to actually find the absolute maximum minimum on 3 separate intervals. So I'll just give you one of these. How about on -2, 3? You know what you need to do? Yep, okay, go ahead. When you have the answer, raise your hand. I'll come by and take a look, see if I concur. I think I'm not even going to mute my microphone. I'm just going to leave it on. You good? Let me just see what you got. Negative 2, 3. Where is it here? I don't know if I got that same thing. Let's see. Negative 2, 3. I'm not getting the same thing. I see it. Check your factoring right here. You pulled 6 out, but you never pulled it out of the 12. So you did your endpoints, and then 2 and negative 1. I think you did 1. Yeah, that's going to change. That's going to change one of your answers. What do you got? So 2, negative 2. These are backwards. This is minus and that's plus. When you factor that, yeah. So that changes. It's positive 2, negative 1. That's going to change your answers over here also. Okay, there we go. Yep, that was good. That's good. What else? Check each other's there. Oh, there we go. There and there. Yes, good. Okay. 31 and yeah. Okay, looks good. I'll be right there. Yep, good. Mm-hmm. Yep. Yes, that's it. Set each of those equal to 0 now. Oh, you already did. Okay, so you got those. Now plug those into the original function, which the original. Yep, always the first one. On this, for what we're doing for absolute maximum, it's always the first, always the original. And if you're going to do it by hand, you have to actually sit there and 2 and then 2 cubed, and it's. I'm going to write the next problem down, and then we'll talk about this. Okay, I think I've given everyone enough time on this one. Your derivative was 6x squared minus 6x minus 12 equals, right? That's it. And then when you set this equal to 0, you should have got two solutions. They were, what, -1 and 2, I believe. And then you're going to plug into your original function -1, plug in 2, plug in -2, and plug in 3. So your two critical numbers, and by the way, I checked to make sure that these were in here, and they both were. And plug those in, and I believe -1, what'd you get, 31? Was that right? -1, you got 31, and at 2, you got 15. Oh, no, 4. 2, you got 4. What about at -2? 20, and then at 15 at 3. So that's what you should have gotten. This one right here will be your max. And your minimum is this one. Okay? Any questions? All right, pretty much everything that we've been doing last week or two has led us to a problem like this, which is actually a very good problem in terms of business, if you want to look at these things from a business perspective, because it's going to illustrate something very important. We have a company that is selling cameras, and they plan to sell X cameras per week. We don't know how many they're going to sell per week. They've determined that the price-demand equation is this. Now, if you go back to 1324, the prerequisite course for this, this equation tells you how the price is impacted by the demand. So if demand is very low, think about this. If demand is very low, if this is a very small number, then your price is going to be pretty high, close to $400. But the bigger your demand gets, so let's say you plug in 100 into this, then that's going to start to have an impact on subtracting something from the price, so your price goes down. The more cameras you sell, the cheaper you can sell them for, right? Make sense? So this has been determined. And then you have a different part of your company that's determined the cost of manufacturing the cameras. So you have to pay the rent for the facility, the equipment, the employees, the electricity, all that, right? And what they've determined is that your cost is $2,000 plus $160 times each camera, all right? So look at the two questions that you're being asked. First one, what price should we establish to sell these cameras at that will maximize the revenue? And then, what price should we sell the cameras for to maximize profit? Now remember, revenue and profit are not the same thing, right? Revenue is just how much money is coming in, and not considering cost at all, right? Just the money pouring into the company. Profit, on the other hand, you take your money coming in and you subtract the costs, right? Which of these do you think would be more important to know, A or B? Probably B. You want to know how much at the end of the day you're going to be having, how much you're going to have in your pocket. Revenue is not how much what's interesting about this is that we may find a certain price that will bring in the most money, but it may not be the price that brings in the most money at the end of the day after we pay our costs. And that's what we want, right? So let's see if we can determine these two prices and see what they are. So you need to know a couple of things from 1324 to do this problem. For doing part A, we need to know the revenue. So do we know how to get revenue if we have a price-demand equation? And I've covered this once before. Revenue is going to be the price times the number of items we sell. All right? The price times the number of items we sell. Isn't that the money that that's going to come in? That's going to be how much we sell it for and how many of them we sold. So do we know an equation for the price? I'm doing part A here. Do I have an equation that gives me the price? Yes, the price is 400 minus 0.4x, right? I'm going to take that and I'm going to multiply that times the number of items I sell. How many items am I selling? X. I don't know how many, right? X. Okay? And then this revenue is then 400x minus 0.4x squared. So all I did there was distributed that through. That's my revenue function, isn't it? I'm going to even write it like this. Revenue is a function of x because there are only x's over here on this side. So if you give me x, right, this will tell you how much money is going to come in. And I would like us to find the maximum revenue. Well, the price that will give us the maximum revenue. So don't I want to know the maximum of this function? Don't I? Now, have I given us a closed interval? Have I told you that we can only sell between this many and this many cameras? I have not, have I? Which means that we cannot use the method that we just did. Oh, I didn't mention we're in another section, sorry. 12.6 is where we are. So now what we do when we're doing these optimization problems, we have to look back on the previous ideas and say, okay, if we're on a closed interval, we're going to do what we just did. If we're not on a closed interval, we have to do what we did before that, which is find local max and mins. Number line, test points, all that junk, right? So for this problem, I've got to do the number line test point junk. With me? So take the derivative, right? What's the derivative of this function? 400 minus 0.8x. So you bring the 2 down, multiply it times 0.4, you get 0.8, and it's subtracted. So that's my derivative function. What am I supposed to do with that derivative? Set it to 0, right? So now I take this, set it to 0. And I'll continue over here. So I take 400 minus 0.8x, bless you, equals 0. And then I try and solve this equation for x. So I'll just do some pretty basic algebra here. I'm just going to move this whole thing to the right side, which makes it a positive. And then divide 400 by 0.8. So if someone can do that for me, I think you get 5,000. No? 500, sorry. 500 equals x. We're not done. Now I need a quick number line. I put 500 here. That breaks my number line up. And I'm going to get 2 test points. What are those test points going to be?
401.
What did you say? 400? Is that what you heard? 400 would work. And then over here? 600, okay. And where are these being plugged into? The derivative, right? Test points always go into the derivative. The only time you ever plug this number into the original function is if we are on a closed interval. So you have to kind of remember that there's 2 different scenarios we can have. Oh, sorry. I didn't need to shut up. Okay, there it goes. All right, so I'm going to do r prime of 400 and r prime of 500. 600, thank you. That was a 6, I don't know. Your eyes are messing with you over there. All right, so I'm going to go into the derivative, into this one right here. And I get to plug in 400 and 600. So all we care about is whether or not it's positive or negative, right? So when you plug in 400 into this, you should get a positive number. So what that tells me, this is a positive number, is that my revenue function is going up here. And then if I plug in 600, I'm going to get a negative number, and that means my revenue is going down. What does that tell me about what's happening at 500? I have a maximum revenue, right? So let's try and interpret this result. At x equals 500, we have a maximum revenue. Right? Maximum revenue. If x is 500. What does x represent again? The number of cameras we sell, right? Manufacture and sell. So if we sell 500 cameras, we will actually bring in the most money. That does not mean we will pocket the most money because we still haven't paid our costs, right? That's part B of the problem. Now, we have not answered the question for part A. What was the question for part A? What is the price that will give you the maximum revenue? This is not the price that gives you the maximum revenue. This is the number of cameras, right? So how do I determine the price? Go back to your price equation and plug this in for x. Okay, so at x equals 500, I'm going to put here cameras underneath this. At x equals 500 cameras, we have maximum revenue. So price needed to maximize revenue is, and I'll have to continue the work over here. I go to my price equation. My price equation was, price was equal to 400 minus 0.4x, right? 400 minus 0.4x. That's my price equation. That's not the derivative. And when you plug that in, what do you get? 200. There it is. That answers part A. If we want to have the most money streaming into the company, we will need to price our cameras at $200. Okay? Now let's just take a guess. Do y'all think that the price for the camera to get maximum profit is going to be more or less than that? Just, it's kind of a guess here. You think it'll be less? Let's see. Okay? Let's see. So let's go to part B. For part B, we're trying to find, right? We're trying to find price which maximizes what? Profit. So we need to look at what the profit equation is. Profit is what? By definition, profit is revenue minus cost, right? Now, didn't we just come up with the revenue equation? Didn't we just do the revenue a second ago? Okay, so I already know what revenue is. My profit is equal to revenue. Wasn't revenue 400x minus 0.8x squared? Check, please. That was my revenue function from part A.
It's not squared.
It wasn't squared here? No, it was when we passed the x through, right? Revenue was when I started